and data science as well. So I was asked by Raffaello to come here and teach a little bit about scientific and high-performance computing. And the first part of the school, the first 2 days, actually were dedicated to set up, let's say, the scene, to give you all the elements to be productive on a high-performance computing cluster, like the one that you have here at the university. And now let's start exploring what does it mean a high-performance computing cluster, and the best way to exploit it in terms of performance and in terms of scientific productivity. That's actually the goal that we have. First, before going on further, I would like just, I was here on Monday and I didn't see this, but I would like to have a first feedback from the audience, just to understand a little bit your background, your experience, and so on. So in order to let's automatically tune my presentation and my exercises, and also the Luca presentation and exercises with respect to you now. So if you just tell me your name and your affiliation, what are you doing, and why are you using the high-performance computing cluster? Let's start this way. So, Piero.
I'm coming from engineer community, but I also work with computational biology. So I'm interested in high-performance computing.
Are you an user of the cluster right now?
Not now.
Not now. Okay, perfect. Your preferred programming language?
I use C++, a little of Fortran, and then MATLAB.
Okay. Okay, thank you.
I'm Alessandro, and I'm a cosmologist.
You are a
cosmologist.
Okay.
I mainly use it for Bayesian analysis, so Monte Carlo.
Do you write your own code, or do you have written in C, C++? C. Okay. You are an user of the cluster, so you know the cluster quite well. Okay, perfect.
Hi, I'm Morena. I'm a PhD student in math.
Uh-huh.
My research area is computational hemodynamics.
Computational?
Hemodynamics.
Okay, great.
I'm a cluster user.
Uh-huh.
I use it to run my simulations. I have a C code.
Did you write by yourself the code, or something that is coming?
No, I just changed some.
A little bit. And which is the code that you're using? What's the name?
It was written by my professor.
Okay. Okay, so it's not a public domain code.
No.
Okay, okay, great.
I use also Python and MATLAB.
Okay, perfect. Thank you.
My name is Eleonora,
Uh-huh.
and I'm an engineer, and I'm doing PhD in Louisiana.
Uh-huh.
I'm not doing scientific and high-performance computing as I'm an experimental, but he's working with me, and he's doing the
Computational part of your work.
part of my work. So I came here to start understanding.
Perfect. Great approach.
I'm a physicist. I'm also doing PhD with her in her same department. I work mostly with molecular dynamics and density function theory with lamps and quantum espresso.
Okay.
I use clusters. I use the cluster at the university here, and also the Meccanica machines. I have some experience working on clusters.
Okay, perfect. Thank you very much.
I'm a PhD student in computational mechanics. I write my own models in C++.
Uh-huh.
I use the cluster, but without threading.
Without?
Without parallelizing.
Okay. Lot of jobs, independent jobs, or just one single job?
One job that sends a lot of
Thousands of. That's the right way to go. Actually. Giuseppe.
My research in hydrology. I'm currently using the cluster. I'm running some C code, but I'm familiar with Fortran as well and Java. And I'm using also R.
Okay, perfect. Thank you.
I'm Gianmarco. I'm a PhD student in computational biology.
Uh-huh.
And we have our own clusters, which are more or less the same, but they do not have nodes, I think, and they do not have queues, so it directly executes.
So it's not a cluster. It's a bunch of machines put together. Okay.
And I used to use it. I use mainly R for my daily work because I study statistics and
Okay, but you are interested in using now the cluster in a different way, or?
No, I'm using, there is a bottleneck in the first part of the analysis of biological data, which is basically on the alignment of sequences,
Ah, okay.
which is very demanding.
Okay. What are you using? Your own written code or something?
No, there are well-established tools.
Yeah, fast queue and
for
yeah.
compressing and
Uh-huh,
aligning but parallelizing them and be efficient in writing and reading the outputs, I think would make a big difference.
Yeah, sure, for sure. Yep.
So I'm Samuel, I'm a computer scientist and I'm working on my PhD in computational biology. I work mostly on Python,
Uh-huh.
some C, and I'm looking into Julia.
You're looking into?
Julia.
Ah, okay, Julia. Okay, great.
I'm not using the cluster now, but I want to use it for my statistical analysis because I have complex knowledge of it.
Okay. Thank you.
Roberto Bellini, I'm a neurologist too.
Ah, okay.
I'm doing simulation of transport processes in porous media using stochastic modeling.
Uh-huh.
So I'm using the cluster just for doing Monte Carlo. So I just repeat
Yeah, yeah.
several Monte Carlo realizations and I get results.
The right way again. Yeah.
The simplest.
The simplest but the most efficient way,
Yeah,
of course,
yes,
to do the cluster.
And,
Okay.
I'm programming in Fortran, basically
Okay.
only Fortran.
Great.
I not C. I have a very rough knowledge of C,
Uh-huh.
and I'm in Python just for developing.
The prototyping of.
It's more handy for
Mhm.
developing.
Okay, great.
I'm Mirko Pauletto, and I'm in the IT staff of engineering faculty.
Ah, okay. Yeah.
And I'm mainly interested to give support to other users, but I'm not a user of the.
You are the maintainer from the maintainer
No,
side.
They are the maintainer. I'm just trying to glue.
Okay,
things
the
together
two communities.
and,
Okay.
to get more acquainted with the arguments.
Okay, great. And so the maintainer, Marco?
Yes, I work with Michele. We are maintaining the cluster. Basically, we help our users to just be able to do what they need to do on the cluster. We
Yeah,
install software,
okay.
set up the-
So you are the two guys that maintains the cluster, that set up, configure, install the software, and so on and so forth. You did it for us. Thank you very much. Okay, and okay, great. So you will help us in understanding the details of the configuration if we are lost and whatever. Yeah. Okay. Great. Okay. So now I just received a message from Luca that is coming. Okay. But now what we plan to do, then Luca maybe will change everything again, but I mean, so today we will focus on optimization. So we will explore a little bit the cluster. We start exploring the cluster, but we will focus not just on the cluster itself as a whole, but just on the single component, the computing node, okay? As you know, the cluster is actually a way you submit a job. When you submit a job, means that you ask for a number of computational nodes. The number can be just one, because here on this cluster you have quite powerful nodes, a lot of CPUs. And so we will go into the node and we will remain within the node. And actually, we will remain not only within the node, but we will remain within a single CPU. Okay? And we will learn a little bit about the CPU, how the CPU is done, which are the tools and which are the components of the CPU that allows you to optimize and to exploit the power of the cluster. Today we will do that. So this morning Luca will teach you about the CPU, how the CPU is constructed, all the elements, the memory hierarchy, the superscalar pipeline, the vectorization, and so on and so forth. And then we will show you a few tools, Liquid, gperf, gprof, valgrind, whatever, that allows you to understand how your code is actually exploiting the CPUs. Okay? This will be the task of this morning. And in the afternoon, we will play with a lot of small examples, well, with a few small examples, just to understand and to familiarize with the tools and with the results that you can get out of the tools. So this is the first day. Tomorrow, we will move a little bit, we move on with our journey, and we will focus not just on a single CPU, but on a multiple CPU, again within one single core, one single node. And so this we will do multi-core, multi-processing, okay? And then shared memory approach, and a little bit of OpenMP approach. How many of you are familiar with OpenMP? You heard about that, okay? You know that OpenMP is a way to parallelize your code. So today we don't we don't explicitly parallelize anything. We will rely on the CPU, on the compiler, on the tool to exploit parallelization, okay? So parallelization comes for free today. Tomorrow parallelization comes on your own on your shoulder, and so you have to learn how to parallelize. And we will parallelize within one single node, again with the with the shared memory approach using OpenMP as a tool, okay? In the afternoon, tomorrow there will be a little bit of, tomorrow morning, here is Luca coming, okay, Luca. I took the chain just to prepare a little bit and then on. So tomorrow we will in the morning we will learn a little bit about to write a parallel programming using OpenMP, and in the afternoon we exploit this what we learn. We apply what we learn in the afternoon, doing again a little bit of exercises and trying to understand the best way to use OpenMP on the cluster. And also trying to use again parallelism for free. What does it mean, parallelism for free? It means that you don't have to write your own parallel code, but you have to rely on tools that have already parallelization inside, like for instance mathematical library already parallelized by OpenMP by someone else. Okay, so for this we will play a little bit, a few examples and so on, and we will do this kind of activity. Finally, the last day, okay, we will move on multi-nodes, okay? And so we will learn how to parallelize a code that actually share more than one single computational node. And this will be done by means of MPI, that is message passing interface, okay? That is a standard that we will present and we tell you a little bit about, and we will start writing our own MPI program and we will try to use them. Okay, and in the afternoon we will do some exercise about that. A couple of caveats, okay. Generally the material that we are presenting here in 3 days span the whole course in Introduction to High Performance Computing at our Master in High Performance Computing. That is actually a 2 weeks intensive course of 8 hours a day, okay, for 2 weeks and a half sometimes. So material will be shortly compressed and reduced, okay? So this is actually just an introduction. I ask you to present yourself just to allow you to interact. We would like to do something very interactive. We don't wanna, we don't wanna teach in the standard way. This is actually, you are mainly PhD students or researchers, so you are acquainted with a different approach. We are not just teaching, so you are actually welcome and forced to ask questions and to interrupt us as many times as you want, okay? No limit about that. There are no silly questions, only silly answers, so don't be shy on that. Stop us if anything is not clear. We would like to give you a little bit of information. We don't think that in 3 days we are able to make you to transform you in a bunch of nerds that are able to optimize the very last bit of their application, of course, but at least to give a little bit of feeling how things can be done on a cluster, okay? So I think that from my side is all. Luca, I told them, then you can check. I told them that today we start our journey looking at the CPU. Okay, exactly. So tools to optimize the code within a single CPU. No parallelism today, apart from parallelism that is actually inserted in the CPU itself. Okay. Any question, any comment on that? By the way, if you don't do question, I mean, we feel uncomfortable because it means that nothing is clear. So you have to ask things, okay? Don't be shy on that. Luca, you have the slides?
Yes.
Yeah,
I'm
okay,
just
good.
going
And we go for 1 hour. At 10:30 is the coffee break for a quarter, 20 minutes, and then till 12:30, correct?
12 here.
Ah, till 12. Okay.
1
One from.
again on
Okay. Okay. Perfect.
4:30.
Sì, molto trentino a 12. Ah no, questo devo darlo a te.
All right. Okay. Is that needed? Because you are registering?
Yeah.
Ah, sorry. Okay. Hope I'm able to use this. Yeah. So, okay. So, as first, my apologies for being late. I wasn't able to find exactly the place. So, I'm Luca Tornatore. I'm working at the National Institute for Astrophysics. Actually, what I'm doing is I'm an astrophysicist, but since about 20 years, I'm dealing with numerical cosmology. So, basically, high performance simulation of the galaxy formation, structure formation, astrophysical processes, and so on. And what I'm talking about today is the modern architecture of the CPU and what it does mean to profile and optimize a code on this architecture. Okay. Yeah, kind of draft of this because in just a couple of hours it's really impossible to give you a comprehensive course, of course, but just a kind of map so that you can move in the map and by yourself then go deeper in detail, okay? So, actually, of course, high performance computing requires by name itself to squeeze all the performance that you can on the machine you are running on, okay? So different machines have different features, okay? So that is important. That's why it's important that you understand what is the architecture you are running on. And actually, optimizing is just, I would say, a flag, okay? Kind of tag. So just try to define optimal. What does it mean optimize? In your experience, I'm not, of course, this is not an exam, no? It's just, I'm trying just to wake you up because you fell asleep waiting for me.
Trying to get to your result with a minimal investment, economical investment in the system that you are using.
For instance.
Or the energy that it uses to compute your
Absolutely, that is a key factor. Tomorrow we will see about that exactly. So, actually, just to be short, okay, so optimization means a lot of stuff, no? Of course, normally, so this is the first thing that you think of, okay? So time constraint, you want to be faster, okay? But actually, it depends on what you're doing and where you are. You may as well have memory constraints, okay? You may have energy constraints. For instance, if you are writing a code for a satellite, a satellite has very limited resources because its weight must be really controlled, for instance. No? So you have strong energy constraints. I worked for a satellite, an astrophysical satellite, and all those constraints are really, really tight and put under pressure the code that you are developing. Okay, so optimization, mission critical software. So an optimal software is not, in this case, the fastest software, but is the most robust software possible. Okay, so that is, under every stress condition can be resilient. Okay, for instance. So optimization actually means a lot of different stuff. Okay, and most of the time, many of this together at the same time. So, but as Knut said, Knut is the famous author, for instance, of LA Tech or whatever, no? So, just go, with a little bit of salt. For instance, the first optimization is that your code is correct. This is kind of cultural introduction to hacking, okay? But the first optimization is that your code is correct. A fast code that gives you an incorrect answer is not optimal in any way, okay? And you most probably will want to reuse the code, okay? So it has to be readable, maintainable, and well designed, okay? This is optimal. When you spend months in trying to understand what the hell that code that you wrote 5 years ago is doing, this is not optimal in any way, in any case, okay? And probably also other can want to use, probably will use your code, okay? So it must be not obscure, non-redundant, and so on. So the first steps to consider is to have a cleaner code, to redesign some fundamental architecture, and to improve and just at that point to improve the workflow, okay? So be dry, don't repeat yourself. It's my experience, personal experience, cut and paste, okay, to reuse some code, blah, blah, blah. But this increases the amount of needed work to maintain the code, either debugging or updating. I spend a lot of time in my 500,000 lines of code, not just mine, because we are a group, blah, 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 because a lot of cut and paste. And then you discover a bug, or you improve something, and then you have to replicate in many other places, and something like that, okay? So be dry, because otherwise you have a lot of what is called technical debt, okay? You try to search on Google, not time to be, this is really software engineering stuff, but it's something quite interesting. And readability. Write a readable code. It means well-structured, with a lot of comments, with modular design, okay? This is the first steps to be optimal, okay, in several sense. Write comments, okay? Really, write comments. And as for the design, you have a kind of top level, which is the algorithm that you choose. This is absolutely the first ingredient of your code, okay? You have a problem, and you have to choose an algorithm. And at the same time, to choose a data model. These two steps are the most fundamental ones, okay, that you can have. And okay, this is kind of level view from abstraction to coding details, which is basically the same that I'm just saying. Okay, I'm just going through. Okay, but then I give you, of course, the slides, just a kind of cultural introduction, as I say. This is really important. Testing is part of the design. You have to write your code from scratch at the beginning with testing in mind. Unit test and integration test. Unit test is when you separately stress each unit of the code. That means that every unit must be quite small and, if possible, just perform one task. Okay? A unit means a function, a procedure, whatever it is, the language that you are using, means one stuff. Then you can stress that unit of code under whatever condition and be sure that it behaves correctly. Okay? In error condition, in optimal condition, whatever it is. So this is called unit test and must be in your code from the beginning. And then you have the integration test, so you stress the integrated behavior and all the run paths that you have. In normal code, you have a lot of different run paths, okay, under different initial condition or whatever it is. And you want to stress all of them and to cover all of them and understand and verify that all your units integrated with each other behaves correctly, okay? This is called this integration test. And then the system test is how all these behave on the machine you're running on and on the system you're running on, okay? This is really part of the design, as well as validation and verification of your code, okay? This is kind of something that I have to force myself because I'm not a software engineer, but I had to somehow to learn the hard way of professional software developing, because if you are in a big project, several thousands or hundreds of thousands lines of code, you really need from scratch to understand that this is part of optimization, okay? Because it saves you a lot of time and ensure you as much as possible about the correctness of your code under whatever condition, okay? So, and then improving workflow, memory imprint, blah, 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 and this is exactly the focus that we have. So, end of the cultural introduction. So, this is the first part of the talk. So, modern architecture and optimization, then profiling and debugging. Part of this will be moved to the afternoon with some exercise, okay? So, modern architecture. Everybody knows about von Neumann architecture. Actually, I don't know why you're software engineers, and so you probably know much better than me. But the point is that basically, here are the main points of this architecture. So you have one processing unit. Oops, I lost my voice. You have one processing unit, okay? One instruction is executed, sorry, this is one answer, is executed at a time, and memory is flat. So this is probably the most important point here, so that the memory is flat. Means that you access any location in your memory at the same cost. Oops. Any expert? Because I can write a fast code, but not use this. How did you succeed, Stefan? Well, whatever. So let me find kind of optimal solution like this. Well, quick and dirty fix are legal sometimes, right? Fine. So then memory is flat. This is extremely important. So means that accessing any location is the same as for the cost. What is cost, then we'll see. And that has access to memory has the same cost than executing an operation on your processing units. This is basically what, as for us, a von Neumann machine is, okay? Today is totally different, of course. I mean, much more complicated. So you have many processing units, which is the focus of tomorrow, actually. You have that many instructions can be executed at a time, and that many data can be processed at a time, and instructions are internally broken in many simple micro ops that are pipelined. It means that different instructions could have quite different costs. Yeah, in von Neumann machine, one instruction, one unit costs, more or less. Okay? So, and this is also a quite different feature. And memory is strongly non-flat. So it means that there is a strong memory hierarchy. Yeah, cost here means CPU cycle. Okay, when I'm talking about cost, I mean how many CPU cycle you spend on whatever it is. And the accessing memory can have very different costs, depend on the location. Yeah, this has been screwed up, sorry. These ones were the asterisks for cost, okay, sorry. And accessing memory is way more costly than performing an operation on your CPU. Okay, so these are the main differences, and in any case, the ones we are interested in, okay? So in the next slides, we'll go through all these features in chronological order. So trying to understand why they developed, okay? But not really why. Why is actually part of tomorrow, because I want to stress tomorrow why we are in such dire conditions today and why they are here to stay, okay? So This is what we will have in the next decades, probably, okay? So that's kind of overview. So you have, in a socket, you have many cores, and then many threads per core, and super scalability inside each thread, and pipelining inside each thread, and vectorization, okay? So this is kind of a hierarchy of what is the modern architecture today. So, early 90s, CPU got faster than memory, more or less, okay? It was a little bit faster even before, but I mean, so this is from a 1997 paper, and you have the clearly, I mean, the CPU is faster than the memory. So the point is that the CPU may spend more time waiting for data coming from the memory than executing ops. This is called memory wall. That's a problem, of course. You can understand this. So I want to perform an addition. So I have to call to data, no? And for the addition, it's 1 second, and 100 seconds to wait for data. Then I have to perform another addition, so I'm spending 200 seconds for waiting for data, and 2 seconds performing operation. This is not optimal in any way, of course. No? So that was the problem. So what's the solution? Of course, you know, solution is to keep your CPU with a faster memory, which is called a cache, and that is electronically different than the RAM, but is also much more costly in terms of dollar in this now, and more energy consuming. So in any case, it must be basically small, okay, for a number of reasons that we'll see tomorrow. So we have also a hierarchy in the cache, as you know. There is level 1, level 2, level 3, most often. Okay, and then there is the RAM. I mean, this is more or less how many cycles you spend. It depends. There's kind of variability from CPU to CPU, but more or less this is the order of magnitude. So 1 cycle to access a register inside the core, and couple of cycles to access level 1 cache, and more or less 10 cycles for level 2, and then you may have 30, 40 cycles for level 3. It depends, a little bit less today, and more or less 100 cycles for the RAM. So there is a strong hierarchy, okay? So where will you put the data? No, that's the point. Let's give an example. Let's say that we have just the level 1 and the central memory. Let's say that we have 100% hit to level 1, so all the data are in the level 1, and so accessing memory in average costs 2 cycles. Fine. If you have 99% hit, which is, I mean, a large figure, no? Then actually it costs in average 3 cycles. If you have 97% level 1 hit, then you have 5 cycles. I mean, 50% to 150% slower in terms of cycles, okay? Just to access the data. So let us introduce level 2 then, okay? Which is a little bit slower in access time, but save us a lot, okay? Because now if you have 90% level 1 hit and 97% level 2, which is normally much larger than level 1, okay? So level 1 normally is tens of kilobytes, more or less today, and level 2 is megabytes, more or less, okay? So quite larger, and it saves you a lot. Okay? So that's why there is the hierarchy, and then we could go on further with level 3, whatever it is, but I mean the point is this, okay? So let me give you an example. So this is quite simple model of cache, and direct mapped 16-byte data cache. And let's say that you are accessing an array. Okay, we are in C. Okay, so row major order. It is clear row major order for everybody here. Okay, fine. If not, just stop me and I go to the Blackboard in a second. Okay. So row major order we are accessing this way, okay? The point is that then you can just go on and try to understand whether there is some error, okay? But the point out here is that you have 50% miss rate. Fine. We change the accessing order, exactly the same loop, and then you have 100%. Okay? Again, and then you have 25%. I mean, the array is the same, the data are the same, I'm just changing how I'm accessing the data, okay? But you now understand, just thanks to the previous example, this can change a lot, okay, by execution time, for whatever I'm doing on the data. Okay, this is very simple example, very stupid snippet of code, not real world, but I mean, the point is this. You have to be, I mean, to care about this kind of stuff when you design your code, when you design your data model, okay? I'll be more clear in a few minutes. So, this is the memory mountain. It's a funny exercise that I taken from Carnegie Mellon, I don't remember. So basically, it's just a cycle exactly like this, not that much different, okay, in which you access with a strive and different amount of memory, okay, and you just measure how much megabyte per second you are accessing, okay. So here is inside your level 1 cache when you fit totally in cache, and here is the death valley of the RAM. So here, just because of the strive that you use, you are continuously jumping to the RAM because you miss every time the level 1, level 2, and level 3. Here, actually, you are hitting level 2 and starting hitting level 1, okay? Here is level 3, and here is the death valley. Just because how you have stored, actually how you are accessing the data in your array, okay? You can see that you have a huge difference, okay, kind of factor of 10. This is on my laptop, okay? This is the memory mountain of my laptop. Yeah, of course, these are the strides in double, okay? And this is the size of the bunch that you are reading in the memory, okay? So the larger the size and the larger the stride, you go in the death valley. Right? Well, just using this kind of stuff, I'll give you the code just to try on your laptops or whatever you want, on your mobile phone, for instance. And you can find out your cache size. This is, again, my laptop. And you can see that these are the miss, okay? As long as you change the stride or the set size, okay? And here, all my set is in the level 1, okay? So you have an array, large, whatever, n, okay? If all your array fits in level 1, when you go through the array, you hit level 1, okay? You never have 0 miss because you have the compulsory miss. That is to say that the first time that I read some kind of datum or whatever it is not in the level 1 cache, okay? It has to be recalled from the memory. So the first read is compulsory miss, unavoidable. That's life. And, well, probably I should have inserted, I didn't want to put really too much stuff, but the point is that your cache is organized by line, okay? Normally, it's kind of 64 bytes, okay? And it is set associative. We will see later on what it means. So the point is that when you access this data here, you actually are transferring 64 bytes from your RAM to the cache, so the entire line. So I'm accessing this. Actually, for free, I have all this, okay? But even if I'm accessing this one, I have all this, because it's kind of mapping. Okay, if you want more details, can give you an exercise time so we can understand how to calculate this kind of stuff. Okay. So the first time that I access one of these data is the compulsory miss. After that, I have the whole line. So better, of course, to access this data, this datum here, right? What happens if, let's say that this is my RAM, okay, which of course is a linear stream of bytes. So let's say that this bunch here is mapped on this line, but also this bunch here is mapped on this line. Of course, because this is 32 gigabytes, and this is 32 kilobytes in total, all my cache. So of course, there is redundancy, right? So in this case, I may have different kind of behaviors, and I have some different lines in which these two bunches can fall in, okay? About 8 normally in these days. After that, if all these 8 lines are occupied, one of these lines must be discarded, flushed. And there is an enormous amount of literature about how to choose it. You are not choosing this. There are algorithms inside the hardware that will choose for you, okay? So you don't have any kind of power in this. It's just to let you understand how it happens. So you read this, you populate this, okay? You read this, you should populate this as first by this occupied. Then you go on the second choice, on third choice, blah, 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 okay? And then if all the choices are occupied, then you go back and you have to flush away one other line, okay? These are some consequences, okay? It is kind of cache resonance, and I will tell you something in a few minutes. So this is, again, you can understand what is the cache size of your processor just with this very simple exercise, okay? So you have to measure the cache miss, and this is my, of course, my cache. This is level 2 and level 1, okay? And this is the cycle per operation metrics, the same as before, okay? The same cycle, the same set of data, but now what I'm measuring is the cycle per operation, okay? So how many CPU cycles it takes to perform an operation, and the operation is this one, okay? So just, it depends. So this is fused multiply addition. Basically, it depends on the CPU, 1, 2, 3 cycles, depends, okay? And so what is dominating is this one, okay? And you see that this has steady increase when you jump from level 1 to up to level 2, okay? Okay, so now let's go for something very simple and very common, matrix transposition. Stefano has a lot of exercise and code about this. And this is the naive version, okay? I mean, just you write down the same that you write in the on your book. The point is that you have a strided access to either A or B. That's unavoidable because you are changing order, no? From row major to column major, or the opposite way, whatever it is. So in one of the two cases, you have a strided access. What I mean by strided access, so now this side just for democracy, okay? So, well, this is your matrix, okay? If your data are stored like this, okay, you are, for instance, in the case of A, I think in that case, you are accessing sequentially, okay? But now you are writing in this way, but even here the data are stored in this way, and so you are accessing with a stride, okay? So, what is better, in your opinion? I mean, as first, there is a difference? Yes, no, maybe? Yes, there is, of course. Otherwise, this slide wouldn't be here, okay? Yeah. Well, it depends, actually, on the architecture. Again, it depends on the policy of the cache. But normally, on the cache that you find on HPC machine, laptops, blah, 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 there is, because of the write allocate transaction, and the strided writes are more expensive than strided loads. I can tell you. So this is the ref means reference. So this is the naive version in which you have strided write. So you are the strided, which is actually what 100% of people will do in first place, okay? So you have a strided write. And this is just the opposite cycle, okay? You have strided access and in order write. And this is the bandwidth. So basically how many time it takes for this cycle to finish you know perfectly how many megabytes you are exchanging because you know the size of your matrix, okay? You measure the time, and you have that the bandwidth is, I mean, this is log scale, okay? So it's much larger. Just because I'm swapping, okay, one of the two strive is, I mean, unavoidable, of course, by definition, in this implementation, which is very naive, blah, 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 okay, whatever it is. But then still, you have this kind of effects, okay? So optimization is kind of puzzle, no? With a lot of very small pieces to be put in order. Yeah.
Here you have a square matrix.
Yeah.
It's not square.
Yeah.
The same.
Yeah, it's square. Yeah.
But in case.
No, in case, yes. I mean, it's the same. Point is that, I mean, it depends on if the matrix, all the matrix fit in your level 1, for instance, you don't have this problem. Or even in level 2. I mean, this problem is really mitigated. The point is when your metric is clearly much larger than your cache. Well, and this lead to another consideration about so the point here is how you organize the data in the memory. This is one of the most important optimization that you can perform. That is why your data model is also important, okay? So you have to think from the beginning, what are your data, what are the relations among your data, and how will you use the data, okay? So let's go for a very simple example, linked lists, okay? So you have, this is the node, one node of your linked list. Of course, you have kind of key that is the identity of your node. And you have the data that are carried by the node. And then, of course, the pointer to the next node. I mean, quite very stupid and naive implementation of linked lists. Point is that how you will traverse the linked list. Okay, if of course, it is safe to access the memory region, you compare the key. Is that the one you're searching for? And then you do something on the data. And then you go on. Or otherwise, you go on. Okay? Fine. And point is that, for instance, okay, here you are comparing the key, and if the node is not the one that you're searching for, then you go to the next one, okay? So actually, what you're doing is to use the key and the next node very close in time, most of the time, because there is one node that you will use, and I don't know how many nodes that you won't use. So actually, most of the time, you're using key and next node close together in time and space, memory space, and not key and the data. So it's first swap, because then here you read the key, okay? And it is in some position in memory. And then you also load in memory 64 bytes. 64 bytes of what? Of this, that you won't use. Then you have to use this one, and then you have a cache miss. You do that for 1 billion times, because you are looking for, okay, if you have a linked list of 1 billion, okay, probably you have to change something in your code, but whatever it is, okay, the point is, then you are wasting a lot of time, okay? You change, and you save a lot of time, just because you have to think what you're doing with the data, okay? I mean, it is not that this one is incorrect in any way, okay? If every time you will use the first 60 bytes of the data, every time that you access the key, this will be correct, absolutely. But there is one more step that you can do. Why in the hell these 300 bytes should be inside the node? Because in this way, a node cannot fit in a level 1 cache. Okay? So you are accessing the first node, okay, the key, fine. Okay, you compare, I'm sorry, it is not the right one. Ah, yes, then I have to go to next node. What a lucky I am, it is here. And then there are 300 bytes of crap. Okay? And then again, I have another miss because I have to call the key. So why not to basically put actually key and next and then a pointer, and then again the key, next, and the pointer. So I have basically a lot of nodes in my cache line. It is easy. I have just to put a pointer here, or whatever it is in the language that you're using, and touch the data. Because this data will be accessed just once in a while. There is no need to put the data there, okay? This is data layout, okay? Design your data as first. This is called hot and cold field, okay, in structure. These fields are hot, these fields are cold. So the touch, hot and cold. This is also, yeah.
All the hot together and all the cold
Exactly.
separated. in
Exactly.
a
The golden rule is what is used close must be close in time, must be close in space. Okay. Okay, so this is, I mean, there will be a lot of to be said about memory, cache, and so on. A lot of materials. If you're interested at the exercise time, we can go deeper in detail. So next step, we were in the early in the 90s. Now we are mid in the 90s, and superscalar and out of order CPUs appear. What does that mean? Superscalar means that you can perform more than one instruction in a cycle, or 2 cycles, or it depends. Okay, so but in any case, more than one instruction are on the fly inside your CPU at the same time. And out of order means that it is not say that the operations are performed by your CPU in the same order that you have written them in your code. But, I mean, of course, the semantic of your code is preserved. Not all the time. There are some cases in which some operations are can be dangerous. So, let's go in order, actually. So, you have basically two, but probably you know better than me, 2 different parts in your CPU. One is the front end and one is the back end, okay? So the front end is basically what is responsible for fetching instruction, decoding the instruction, and dispatching the instructions, okay, to the back end that is actually in charge of executing, okay? The back end has different ports, many than one. That's why it's superscalar. Every port is kind of a door on the corridor in which you have a lot of different units, okay, replicated, because you have logic unit, shift operators, memory operators, and you can have arithmetics, whatever, shuffling, divisions, whatever, okay? So, I mean, then you have vector units or non-vector units. So this is, of course, what is in the hardware. You don't have any power on this. It's architectural choice of engineers, blah, blah, blah. But the point is that you can change the way you program knowing that. So here, the key point is to let the CPU to populate as many ports as possible, okay? Because there are these many ports means that I can perform, for instance, an addition and, an addition and a memory operation at the same time, because they are, I mean, really 2 different physical regions of the CPU separated, so they can work at the same time, okay? The point is that I have to write the code so that it is possible to do that, right? Yeah.
The ports are different in what they can do, or are they all the same?
Both, in the sense that they are different because, as you can see, they are accessing different, I mean, all this pile of units are different, but are also similar, because arithmetic and logic unit is replication of the same, exactly the same number, the same transistors, okay? So they are quite similar. So they are the same in the sense that an addition can be performed in a correct way in more than one port, but at the same time, different ports have a different ensemble of these units, okay? Well, so what is a pipeline? In the 80s, actually, an instruction was not really, but okay, let's say a kind of atomic operation, okay? Well, actually, Stefan and me, we were in a European project with the guy that designed the famous the RISC-2. Okay, so the folder of all reduced instruction set where the operation are monolithic, very simple operations. And but actually nowadays, you don't have this kind of instruction, not in the commodity CPUs actually, and you should think an instruction as made by independent steps. So the execution of an instruction is made by independent steps. So you have, as I said before, to fetch, to decode. So to fetch means to recall from memory. So you populate the level 1 instruction because I mean level 1 cache is separated. One half is for data and one half is for instruction. Okay, because you have cache miss also for instruction. It's not you have to recall. I mean, you have to recall from memory also the instructions. Okay, not just the data. So that has consequences because if you jump in your code continuously, you have a lot of cache miss for instructions. And you get slower, okay? So that's why also I said before, just try to write very small unit of code that perform very well a single task, because then all that code can fit in the cache, right? And try not to branch as less as possible, okay? Branch means that you jump, if then this, go there, blah, blah, blah. Just try to avoid as much as possible. It's a matter of workflow design, okay? So you fetch the instruction, you have to decode, so the front end have to decode the instruction to understand what that bit means, okay? And then to execute means to dispatch to the back end, and then to write back the result, because the result must be written back somewhere, actually. This is part of the instruction execution. And let's say that all the 4 stages takes 400 picoseconds. This is the picosecond is the time scale, okay, inside a CPU for this kind of a transistor, basically time scale. And we will obtain a throughput of 2.5 giga instruction per second, okay, micro instruction. Okay. And actually, 400 picosecond is also the total time required to get a result from an instruction. Of course, it takes I will say, okay, 400 picoseconds, then I have to wait 400 picoseconds, of course. Then I have another instruction, 400 picoseconds. Okay, you may say, oh, okay, 400 picoseconds. Again, what is this? But point is that if we were able to detach the 4 stages, that would be a great advantage. Let's say that there is a guy that is so let's say 4 of you, you have just to fetch instruction. You have just to decode. He has just to execute, and you have just to write back. So you fetch one, and then you're free to fetch immediately another one while he's decoding the first one, and then you pass the instruction to him, and you pass the new fetch to him, and blah, blah. So actually, then at first you have to wait for 100 picoseconds. But then you have just to wait the lapse of time between 2 of you. Okay? This is called pipelining, of course. And then you have a lot of much better throughput. You can have, in this example, 4.5 giga instruction per second. I mean, these are just hypothetical figures, okay, just to make the point. Right? So it seems that you have the key. Fine, okay. Now, if you have 100 long pipeline or whatever it is, and you make better transistor, and then you have what is then driving your performance is just the latency. Okay, if all the stages takes the same amount of time, let's say 50 picoseconds, okay, then what you have is 20 giga instruction per second. An enormous amount of performance. So we have the key. We solved. Okay, just pipeline. Pipeline as much as possible. 1,000 stage pipeline, whatever it is. So because as much as you are able to break down every instruction, as much and then you diminish you can make it smaller the latency between 2 stages, and then you have an enormous throughput. Fine. Well, that would have been nice. But actually, so pipeline is increasing the throughput of the system. Okay, the same system, exactly the same, just reorganized internally, you have much larger throughput. Yeah.
The latency though, how is that hardware dependent or is it also dependent on?
No, it's hardware dependent in this case. Okay, the point is that, I mean, if you can imagine that performing something as a lot of electrons that go around in circuits, okay? If you are able to break down all these circuits in smaller pieces, okay, then the point is that the electrons have to travel much less space, and then the latency is much smaller. Okay, more or less that is the point. Well, then you can have also multiple pipelines, okay, because all these ones can be a pipeline, okay? So you can have not just multiple ports, but multiple pipelines inside a port. So you have very long pipelines, multiple pipelines, enormous throughput. That would be perfect. And this is a pictorial view of multiple pipelines, okay? So you fetch, you actually have also multiple decode and dispatch guys, you have a lot of ports, you can perform integer operation with 3 pipelines, for instance, floating point, testing and branch, memory operation. You can that's why the CPUs get bigger and bigger actually, because they are starting to be they started to be populated with a lot of ports and pipelines, whatever. Okay, but of course, what I put here. Yeah, just to let you understand. So basically, in modern processor, typical figures are 1 cycle of latency for integer operation, 3 to 6 cycle for addition and multiplication, and division is still, I mean, something problematic, 10 to 20 cycles, and for trigonometric operations or exponential logarithm, whatever it is, you go for 50 or even 100 cycles. So that is also important. Try to understand that an operation, an addition is not the same than a division, which is not the same than a sine or cosine or a log or whatever. Okay. And the point is that this latency can be troublesome because for the memory loads, but also for this because, I mean, probably, let's say that you have this log A plus log B, okay? This is 1 cycle, and this is 100 cycles, okay? So you have also to reorganize operations, but we will see something later. And also, memory loads can be troublesome because here you have 2 memory loads. I mean, you say, no, this is just math. No, there are also 2 memory loads, A and B, okay? And if A and B are not in the memory already at this point, okay, you have to wait for 100 cycle to access the RAM if they are close, or 200 cycle if they are distant in RAM. So it means that they cannot fit in the cache. They are not close in memory, so they fall into different cache lines, okay? And so you may have 100 cycle or 200 cycle just for memory fetch. And then, again, 100 cycle for the 2 logs. Let's say 50 because it depends. Are you able to dispatch this in 2 different ports that can perform the operation? It depends on you or not. I mean, when you want to squeeze every cycle from your CPU, you really have to care about this kind of stuff. Yeah.
In that definition, the latency has a different meaning compared with the ones that you were using before in the previous slide, where you wrote that it was 50 picoseconds. Because he says it is the number of stages of the pipeline multiplied by the time it takes to advance one step.
Yeah.
So this definition is not homogeneous with the previous slide, or not?
No, it is not. It is not. Yes, this is in cycles. Actually, they are related in the sense that of course, you know that the time in your computer is discrete, is not continuous, because the transistor have to charge and discharge. You know? So this is dominated by the frequency of your CPU, so the gigahertz, blah, blah, blah. No? So when the latency is measured, expressed in cycle, it is CPU dependent. So you avoid the real time scale. That it could be even 1 second. If you have your CPU as a frequency of 1 hertz, it is 1 second. No? This is a kind of relative latency and performance to your CPU. Okay. Then this was just to give you before it was just to give you a kind of what could be a real example in real time scales. So they are different definition of latency. Actually, I should be thanks. I have to be clear about this, but they are in any case related. Yeah, tell me.
Is this some kind of optimization that now compilers are able to obtain automatically, or is
Yes and no, in the sense that compilers are getting better and better in performing this kind of optimization, in understanding the relations between data and blah blah. But you can easily put them in troublesome. It depends on how you write the code. So that's a good point. In fact, one of the golden rules that I'll show you later is the first optimization is to write the code so that to let the compiler do his job, to do his job. Okay, this is the first implementation, because unless you are becoming really professional, most probably the compiler is better than you. But then try not to, complicate the stuff. Okay, so as first learn how to not complicate the work of the compiler, and then care about all this stuff. Good point. So actually, okay, it seems that with the pipelines we have the solution, but of course we have also hazards. There are 2 types of hazards: data dependency and control dependency. So pipelines are wonderful, but let's say that we have a 4 cycle. Well, let's say that we have an array. Okay, right, this is a pointer actually. Okay, so an array, whatever it is, and a 4 cycle over the array, and then we want to sum up all the elements of the array. Very simple. What's the point? That, the next operation depends on the previous operation. No way to avoid this. I cannot sum up A1 to some, let's say A2, okay, before that A1 has been put on sum. I have to wait. If I write the code like this, I have to wait. So this is data dependency. Okay. Control dependency is a branch. If I'm happy, I smile. If not, no. Okay. So it depends where I'm going. I have to wait for the evaluation of the condition, and then I understand where to go. How can I populate a pipeline like this? No? That's a problem. 2 really big problems that, of course, ruin all the wonderful world of pipelines. That's why we don't have that enormous amount of performance from our CPUs. Right? So if a control hazard arises, the entire pipeline has to be flushed, because your CPU is out of order. It means that can speculate, or what will, it means 2 different stuff. If I have here, let's say, this one inside the 4th cycle, I have this one, and then I have that the ai minus 1 equals 0, for instance, no? Okay, I minus 1 has already been used. I don't need it anymore. So actually, these 2 instructions can be executed at the same time. There's no problem, right? So this is one part of the out of order. The other one is that I can speculate if there is an if A larger than 1, do something else, okay? So I can speculate, trying to understand, while I'm waiting for this evaluation, where to go. And starting to populate the pipelines with the instructions that are either here or here, depending on the result of my speculation. If the speculation proved to be wrong, as soon as this result is available, then I have to flush away my pipelines and to populate the pipeline with the right branch. This costs a lot. And it costs more when the pipeline is longer, okay, of course. Well, best branch predictors are as good as 95% of accuracy, okay, which is quite good, okay. Clap hands for engineers that have this performance. But actually, typical penalty is 10-20 cycles for pipeline flush, at least, okay? Depends on how long is the pipeline. Pipeline nowadays are 10 to 20 stages in commodity CPUs that you have on HPC facilities or your laptop or whatever it is. And for this reason, of course, right? Because the longer is the pipeline, and deeper in the future you have to scrutiny. Let's think it to an example. Let's say that we have a there were pipelines much longer than this, but let's say that we have 140 stage pipeline, and instructions are in the flight, in the pipeline, and 1 every 7 is a branching instruction. Okay. What probability does the pipeline have to be correct if the branch predictor is 95%, have 95% hits, or 90%, 36%, and 12%, so quite low. And this is a figure, an average figure. 1 instruction every 7 or every 10 is a branch. Okay? So even if you have that incredible predictor, you have that incredible inaccuracy. I mean, that incredible amount of penalty. So branch prediction, misprediction is another huge problem in your code. And that's the reason why we don't have 100 stage deep pipelines, because it actually, in real world, I mean, where you have branches, it will cost a lot. So how the pipeline how many stages are in the pipeline is kind of trade-off between the throughput that you want and the real world that you have. Example. This one, okay? So S is both read and write, okay? Because you have to know the value of S, and then you have to write back the new value of S. And of course, you have to read A and B, okay? And you have a data dependency, of course, as I said before. Well, unrolling, that's your question, okay, about compiler. I mean, this code is as correct as this one. Of course, at the end, you have to sum up, sum 0, sum 1, of course, no? I mean, they are correct. Exactly the same amount of operations and so on. The point is that here, you make it easier for both the compiler and the CPU to understand that they can perform these two operations at the same time because they are independent. So here you are populating 2 pipelines, or at least using 2 ports, okay? Just because you are enrolling. Here you separate the load and the multiply, okay? So actually here you have actually you make it clearer for the compiler that these 2 variables, these 2 memory locations are defined, live just inside this scope, okay? And so here you have the recall from memory, okay? And that should be, I mean, easy because they are all subsequent. They should be all subsequent, okay? And then here you start the first multiplying, then you start the second multiply at the same time, because you can, if you are lucky, the data are well put in the memory. And so you start these two, and when they are ready, you sum up, okay? But, I mean, everything is much clearer for the compiler, and this has an effect. I'll show you.
Excuse me.
Yeah.
Modern compiler are already able to optimize this kind of situation.
Not all the time.
In this specific example,
In this specific example, yes.
they are
But still, you can see the difference. We try to play with this.
When we start programming in universities, they always tell us, do not declare variables we're just going to use one time. So that's a lie, practically.
Yeah,
Okay, that's a lie. Perfect.
yeah. Yeah, you can, I mean, it depends, I mean, why they do tell this.
Because you are declaring you are declaring an entire double for that is going to be pointed for with a name for something that you are just going to use one time, and since it's a variable and not a pointer, you cannot delete it afterwards. So you are just creating variables.
I mean, in this case, these are registers. You're not creating anything. This will be put in register. You can even tell the compiler, suggest the compiler with the register keyword that these are just registers, okay? For instance, you're not creating anything here, okay? So you can go farther with unrolling, okay? Or you can go for explicit vectorization, for instance, okay? We'll see something later. Well, what happens on Xeon, whatever it is? So time in milliseconds for, I don't remember how many data. Okay, so this is the original performance, okay? This is with unrolling. This is with a separate load. This is unrolling 4, and this is explicit vectorization. See that, I mean, you can save a lot even with this kind of tricks without the explicit vectorization. The divided line is the time that you take, and this is the instruction per cycle. So which is the opposite than cycles per instruction. Cycle per instruction must be low, and instruction per cycles must be high. So here you see that you have more than one instruction per cycle. Okay, and here you have less than, oh no, okay, even in this case there were some kind of gain. Okay. So branches now. Conditional branches are evil, but unavoidable, of course. You can basically you can have real code without conditions. Okay, it's unavoidable. So they should be avoided as much as possible inside loops. Okay, moving them outside whenever it is possible, which is called loop hoisting. The compilers are very good in performing loop hoisting for you, actually, and but still. Why in the hell to write a code that is obscure and obfuscated and about which the compiler has to perform a lot of trickery to understand what you wanted to do? No, just do that since the beginning, you know. And just remember to avoid avoidable. So, for instance, just I mean these are seems to be all elementary stuff, but piled up together, no, they can have a lot of impact. And you have a cycle for some beginning condition, and that let's say that your E less than some kind of operation, which is fixed, of course. Now it depends, of course, if this limit change as soon as we're ongoing with the loop, okay, fine. But if it's fixed, I've seen a lot of stuff in the code that I've optimized. Why in the hell? Create a variable here, okay, and put that variable here, and you save time just because of this. No? Sometimes the compiler is able to do that for you, of course, because it's not stupid. If you use well the compiler, it can do that. But why? When you write the code, you cannot do that for him. I mean, it's much better, no? Because it's still a machine, okay? It's incredible people that write compilers are incredible people. Still, you are the one that really knows what is going on, right? Then, so you can use pointers to functions instead of selecting a function inside the loops, for instance, this is something that I've seen a lot of times, and this is really interesting. I'll show you an example. So this is something that is quite weird, but I've seen that that was actually a code that should have that will actually perform a lot of operation on a mission critical satellite, a physical satellite, and so there was something like this inside the code. Weird. That's absolutely weird. I mean, much complicated. This is just the example that I've put in the code that I give you at the exercise time. Okay, so what you can do is, for instance, if you have this, a lot of this, you can perform, since, I mean, these cases are fixed, okay? These variables, okay, are fixed. They do not change while you are performing the loop. So you can do something like, something like this. You perform here all this condition, you set the pointer, and just you do that, for instance, okay? There is something here actually that using a function pointer, you have an additional overhead, because calling a function is an overhead, okay? Because you have to switch context, you have all the operation on the stack, you have to, your instruction pointer will jump to another piece of region of memory and so on, but still can be a kind of advantage, okay? Or you can unroll the if tree outside the for, okay? But maybe having multiple for loops can be highly impractical if they are big piece of code, okay? So there is not a Swift knife recipe, but still you have to be aware of this kind of effect, right? So consider this code. You generate some random numbers between 0 and top, okay? Top is whatever you want, a number. And then, for some reason that I couldn't tell you, it's just an example, you want to sum up only the data that are larger than a kind of whatever it is, no? Another number. Fine, simple. The point is that you have an unavoidable condition inside a for loop, and this is unavoidable. How can you avoid this? No? So, what you can do, change the way you think. You can sort the data. Why it is effective? Because then the pattern of the behavior pattern is perfectly predictable by your branch prediction. If this is random, your branch predictor will mess up. Of course, how can you predict something which is true random? You cannot, right? In this way, you have a perfectly predictable pattern of behavior. So it depends what is the trade-off between the overhead of sorting and the gain that you have in this case, okay? But this is an example of the way you can change your mind, okay? Say, no, I cannot avoid this. Well, you cannot avoid, but you can make it better. Or, why not? You can avoid. This is a bitwise trickery machine, blah, 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 so that here inside here, there is no branch condition, because if you want, I mean, just try to understand what this code is doing by yourself. I'll give you the slide, and in the afternoon we can, if you're interested, we can try to understand how it works. So this code basically selects only, of course, the data that are the correct data, but without any branch condition, and it is faster, way, way faster than before. Okay. Okay, so let's go for no optimization. This is for these three codes. Okay. So it's the stupid one, okay, the QSort one, and this smart one, okay. So with no optimization and optimization, these are the run time. So 5 seconds, 2 and 2.8, and then we go for this amount of time, which is incredibly less than before, okay, and the stupid version is competitive, okay? So these are just, fluctuations. These are two different numbers. These one are more or less fluctuations, okay? So what happens inside your code? And again, This is, sorry, I forgot. This is the same than before, okay? But, this one is the same than before, but then is to compare with this one. This is GCC, when you tell the compiler to optimize exactly for that CPU. This is something that, yeah, in fact, I've seen your face. Yeah, so when you optimize, tell the compiler to optimize, but this is true for all the compilers, it tries to optimize for the class of CPU that you're using. So normally is, if you have Intel, this one nowadays, okay? So it tries to optimize for all the CPUs of this type, okay? But if you tell, no, I want exactly for this machine, if you know it, if you have it in your database, okay, exactly for this CPU. Well, something happens then. Huh? This is optimization, actually. Know your tools, okay, how to use them at maximum. You have to optimize also the use of the tools that you have. So, but what happens inside? So, actually, if the branches are simple enough, okay, what happens is your CPU chooses to take the 2 branches, not just one. Why? To limit yourself. You can take the 2 branches, and just at the end, you take the right one. Okay, so you evaluate the conditions, you take the 2 branches, fantastic, and just at the end, you see which one is correct. Ah, this one. Okay, fine. Okay, and that's why your CPU. This is the assembler view. That is how I treat my students at university. Okay, so you're lucky that we have just 1 hour and a half. Otherwise, you have went deeper in details. But then here is that you understand the difference between O3 and O3 with the native instruction, which is basically, yeah, okay, Stefano, tell me that I'm killing you. The difference is that you are using vector instructions here, peculiar vector instruction for this CPU. And so you have 12 instructions to process 4 integer, and here 9 instructions to process 8 integer. So you have basically 3 instructions per integer, and here you have 1.12 instruction per integer. That's why it's much faster. Okay. Break.
No?
Yeah.
Did you complete branch prediction or still have
I don't remember. Yeah. Let's say that we have. No, we don't. I don't, but.
Yeah, we can do it.
Yeah. Ma c'è sta una presa elettrica da sé, eccola qua. Ci sta un caffè da questa parte?
Sì, c'è un posto.
No.
Che sia, è lo stesso posto della
È abbastanza chiaro perché sto comprimendo un sacco di cose.
Dipende dal background
Vabbè,
del tuo scontro. Comunque
spero, insomma, dopo magari ripeto, cioè fermatemi se dico cazzate o se non è chiaro.
Fagli un po' di domande, perché se li spaventi troppo poi...
Di sotto. Sono venuto via da questo.